All right, let's dive right in. Today, we are pulling back the curtain on the world of artificial intelligence. We're going to take 20 of the most common and, let's be honest, sometimes confusing AI concepts and break them down with simple analogies so they actually make sense. Yeah, if you've ever felt like you're just drowning in terms like transformers, vectors, or RAG, you are definitely not alone. It feels like a whole new language, right? But don't worry, by the end of this, you're going to feel a lot more comfortable. We're going to clear the fog and give you a simple path to understanding. So here's our game plan. We'll start with how AI even begins to understand our words. Then we'll get into how it learns to think. After that, we'll see how we make it smarter, see it in action, and finally look at how we're building faster, more focused AIs. It's all going to build on itself, one step at a time.
First up, let's get right down to the absolute basics. How does a machine look at a sentence you type and make any sense of it? It's a pretty cool process that starts by, well, breaking everything down into tiny little pieces.
It really happens in 3 key steps. First, you have tokenization. This is literally just breaking a sentence into puzzle pieces, words or sometimes even parts of words. Next comes vectorization. This is where each piece gets a secret number code. And this code, we call it an embedding, is super important. It's what places words with similar meanings, like king and queen, close to each other inside the AI's giant map of language. And finally, there's attention. This helps the AI focus on the most important words to figure out the real meaning, just like you would when reading.
Okay, so now the AI can read, but how does it actually learn to think, predict, and generate language on its own? This is where we get into the brain of the operation, the models and learning methods that make it all possible. At the heart of it all is the large language model, or LLM. The best way to think about it is like a robot that has read a truly massive library, basically the entire internet. And because it's seen so many patterns in how we write, its main job is just to predict what word is most likely to come next. When you type "the early bird gets the," it just knows the next word is probably worm. That's an LLM in its simplest form. Now, this slide right here clears up a huge point of confusion. What's the difference between a transformer and an LLM? Well, think of it this way. The LLM is the car you actually drive, the final product you talk to. The transformer is the powerful engine inside that car. It's the specific algorithm, that breakthrough from 2017, that uses the attention mechanism we just talked about to understand context so incredibly well. So how in the world does this giant model train on all that text from the internet? It uses something called self-supervised learning. The wild part is, instead of a human teacher grading every single example, the AI basically creates its own puzzles. It'll take a sentence, hide a word, and then try to guess what it is. By doing this billions and billions of times, it learns the patterns of language all by itself. It's super efficient, and it's what makes these massive models even possible. All right, so a base model that's read the whole internet is amazing, but it's a generalist. It knows a little about everything. What if you need a real expert? In this section, we'll see how we give AI more specific knowledge and up-to-the-minute context to make its answers actually useful. The first way we do this is called fine-tuning. So if that generalist robot needs to become a world-class expert on, say, medical knowledge, you don't start over. You take the base model and you just keep training it, but this time on a very specific data set, like thousands of medical textbooks. This fine-tuning process is what turns a jack of all trades into a master of one. But what if you need to add knowledge during a conversation? There are a couple of clever tricks. With few-shot prompting, you just give the AI a few examples of what you want right in your question. It's like saying, here are 2 examples of a good summary. Now, summarize this for me. And then there's Retrieval Augmented Generation, or RAG. This is a game changer. When you ask a question, the AI can instantly look up relevant, up-to-date info from a private database, like your company's internal documents, and use those facts in its answer. So you might be wondering, how does RAG find that information so fast? It uses a vector database. Remember those embeddings, the secret number codes for words? Well, this is the magic library where all those codes get stored. When your question comes in, the AI turns it into its own number code and then searches the library for documents with the most similar codes. That's how it finds the most relevant facts almost instantly. It's the high-speed search engine that makes RAG work.
We've seen how AI reads and learns. Now, let's look at how it goes from just answering questions to actually doing things in the real world. This is where things start to feel a little bit like science fiction. 2 big ideas here.
First, the Model Context Protocol, or MCP. You can think of this as a universal language that lets an AI talk to other computer systems and use them as tools, like asking for the current weather or checking flight prices. This ability to use tools is what makes the next concept so powerful: agents. An agent is a program that can use tools like MCP to handle complex, multi-step tasks all on its own. You could tell it, plan my vacation to Italy, and it could go find flights, book a hotel, and put it on your calendar without you lifting a finger. Now, to make sure these agents are actually helpful and do what we want, we use reinforcement learning. Just imagine that every time an AI gives an answer, a human gives it a thumbs up or thumbs down. A good answer gets a +1 point, a bad one gets a -1. Over millions of examples, the AI learns to generate responses that maximize its score. It's just like training a dog with treats. It learns to do more of what gets it positive feedback.
To solve really tough problems, we're building reasoning models, and a key technique here is called chain of thought. Instead of just asking the AI for the final answer to a complicated math problem, you actually train it to write out every single step it took to get there. By learning to show its work, the AI gets much, much better at complex logical reasoning and is way less likely to make silly mistakes.
And, AI is not just about words anymore. We're now in the era of multimodal models. These are AIs that can understand and generate information across all different formats or modes. We're talking text, pictures, audio, even video. You can show it a picture and ask it a question, or describe a scene and have it create a photo for you. This makes AI so much more capable. Okay, for our final section, let's get practical. Those huge AI models are incredible, but they're also really expensive and slow to run. So how are engineers making AI leaner, faster, and more accessible for everyday businesses and tasks? Well, a big part of the answer is small language models, or SLMs. These models are not trying to know everything. Instead, they are tiny, super fast AIs trained to be experts at just one specific job, like handling customer service chats for one company. They use way less power, they're cheaper to run, and they can be incredibly good at the one thing they're designed to do. So how do you create a smart SLM without training it for years on the whole internet? You use a process called distillation. And the analogy is perfect. You take a huge, powerful teacher AI and have it train a smaller student AI. The student learns by trying to copy the teacher's answers, basically absorbing all the most important lessons and patterns into a much smaller, more efficient package.
And our very last term is quantization. This is a really clever optimization trick. The thoughts inside an AI model are basically just a bunch of numbers. Quantization is the process of making those numbers less precise, kind of like rounding 3.14159 down to just 3.14. This shrinks the size of the model dramatically, which means it can run way faster and even fit on your smartphone, all without losing much of its smarts.
So there you have it, 20 core AI concepts, all broken down. From tokens and embeddings all the way to agents and distillation, you now have the vocabulary to really understand what's going on in this incredible field. So the only question left is, now that you speak the language, what are you going to build, question, or create?